All right, greetings, scholars. We're continuing our exploration on Chapter 3, Functions, and here we're going to be closing out Chapter 3, working on Section 3.7, Inverse Functions. A few learning objectives here. In this section, you will verify inverse functions, determine the domain and range of an inverse function, and restrict the domain of a function to make it one-to-one. Find or evaluate the inverse of a function. Use the graph of a one-to-one function to graph its inverse function on the same axis. So an inverse function, for any one-to-one function, f of x equal to y, a function f inverse of x is an inverse of f if f inverse of y equals x. This can also be written as f inverse of f of x equals x for all x in the domain of f. It also follows that f of f inverse of x equals x for all x in the domain of f inverse, if f inverse is the inverse of f. I know that was a lot. We'll come back and re-articulate that. The notation f inverse is read f inverse. Like any other function, we can use any variable name as the input for f inverse. So we'll often write f inverse of x, which means f inverse of x. Keep in mind that f inverse of x does not mean 1 over f of x. And not all functions have inverses. So that initial part was basically to verify that one function is an inverse of another. We have to use composition of functions. So like, say we have two functions f and g. If we consider f of g of x, or f compose g, and the output is x, and then if we reverse the order where we do g compose f and the output is still x, that's how we verify that two functions, one function is the inverse of another. Okay. So if for a particular one-to-one function f of 2 equals 4 and f of 5 equals 2, what are the corresponding input-output values for the inverse function? So because the function is one-to-one, that means that it has an inverse. So then if f of 2 equals 4, then if we did f inverse of 4, that'll give us 2. And f inverse of 12 will give us 5. Okay. That's fine. So given two functions, we want to test whether the functions are inverses of each other. So again, you say f of g of x equals x, and g of f of x equals x, then we can say that one function is the inverse of the other. Okay. So given this f and this g, is g the inverse of f? Okay. So in order for g to be the inverse of f, when we do f of g of x, we should get x, and then when we do g of f of x, we should get x, right? So let's first consider f of g of x. Okay. So this is gonna, now what's our g of x? G of x, let me see. G of x is 1 over x minus 2. Okay. So then what we're going to do is write f of x like normal, but each x in f of x we're going to replace with the green thing. Okay. So we have this x plus 2 under 1. Right? But we said we're going to replace each x with the green thing. So we got this 1 over x minus 2. Okay. Now we can combine like terms. We don't have to distribute, so we can actually lose the parentheses there. The negative 2 is going to cancel with the positive 2. And then when we say a fraction divided by another fraction, we do keep, change, flip. And ultimately, this result is just going to be x. Okay. So now let's consider g of f of x. We need to reverse the order. G of f of x. Okay. So that's going to be that's going to be g of, now f of x is 1 over x plus 2. Okay. So what we're doing is writing g of x like normal, but replacing each x with the fuchsia thing. Let me give myself just a little bit of space. Okay. So g of x is 1 over x minus 2. But our x in this case is this fuchsia thing. Okay. So if we say a fraction divided by another fraction, in this case we can do keep, change, flip. So then this is going to be the same as x plus 2 minus 2. Then these guys are going to cancel. And we're going to be left with x, right? So we did f of g of x. We did f of g of x and we got x. And then we did g of f of x and we got x, right? So then now we can say that g is indeed f inverse. Yeah, so that's fine. So if f of x equals x cubed and g of x equals x over 3, is g the inverse of f? Okay, so same kind of deal. We need to do f of g of x and get x, and we need to do g of f of x and get x. Let's see. So first we're going to consider f of g of x. Okay. So that's going to be f of, now g of x is 1/3 times x. Okay. Now f of x is x cubed, so that quantity cubed. Okay, it looks like it's not working out, right? Because if we cube it, we're going to get 1 over 27 x cubed, which is not x, right? It doesn't cancel out. So that should be enough, which is, and I'm going to say, hey, this is not equal to x. So then is g equal to f of x? We would say no. Yeah. So the functions are not inverses. Okay, we're fine. Let's keep going. So with this, if you have a function f of x, you have your domain, which is your set of input values, and it maps to your range, which is your set of output values. Then suppose that function f has an inverse, then the domain of the inverse corresponds or matches with the range of f, and the range of your inverse matches or corresponds with the domain of the original, right? So the domain of the original matches the range of the inverse. The range of the original matches the domain of the inverse, right? Okay. Because again, the inverse takes your output functions and uses those as your inputs and basically takes you back to your original inputs. Your original inputs now become your outputs, right? Is it possible for a function to have more than one inverse? That should be no. No. If two supposedly different functions, say g and h, both meet the definition of being the inverse of a function, then you can prove that g equals h, right? Okay, so on and so on. Oof, what's this? So the range of a function is the domain of the inverse function, and the domain of a function is the range of the inverse function. Okay, I'm just gonna let you read. Let me read it real quick. Yeah. Let's just do this. So identify which of the toolkit functions beside the quadratic function are not one-to-one, and find a restricted domain on which each function is one-to-one, if any. The toolkit functions are reviewed in table 2. Okay, we restrict the domain in such a fashion that the function assumes all y values exactly once. Are not one-to-one. So if you think about like one simple way to kind of identify whether a function is one-to-one is to visualize their graph or look at their graph. If it passes the horizontal line test, then it is one-to-one, meaning that no matter where you draw a horizontal line, it only touches the graph once. If you can draw a horizontal line and it touches the graph more than once, then it's not one-to-one. So I think for like the constant function, I'll just highlight it. Let's see. And this will suffice. So which ones are not one-to-one? So in other words, they will fail the horizontal line test. It should be this one. Go to style. Actually, I kind of wanted this color. That doesn't need to be like that. This color. Okay. Identity is a diagonal line, so that one should be okay. I know it said besides the quadratic, but I'm going to just go ahead and identify the quadratic. Cubic would pass the horizontal. The reciprocal function, I think, would pass the horizontal line test. I think this one would fail. Paste. Oh, what is that? How do I get rid of that? Oh my God, please go away. Oh, shit. It looks like it's not going away. I have no idea how I put this on the screen. How do I get rid of this? Man. I guess that works. I just dragged it off screen. That's it. There we go. Oh, let's get rid of that. Copy. Okay. Paste. So that one should fail because that one, I want to say that I think it'll fail the horizontal line test if my memory serves me correctly. Cube root is like a elongated sideways S. I think that one passes the horizontal. Square root passes the horizontal line test. Absolute value fails. All right. So in addition to quadratic, we got 3 additionals that should fail the horizontal. Let's see, how do we do? The constant function is not one-to-one. There is no domain except a single point. Okay. The absolute value function, oh, we forgot to restrict. Okay, well, that's fine. The absolute value function, if we restrict it to the half interval from 0 to infinity, then that would basically remove the left half and only keep the right, and then it would pass the horizontal line test. And the reciprocal squared, something similar. To remove the left hand side, we restrict the domain to the open interval from 0 to infinity, and that would basically remove the left hand side and only keep the right. Okay. So that's the absolute value, right? There's the reciprocal squared function on the right hand side. Well, constant is showing, but it should be a flat horizontal line. So a function f of t is given in table 3, showing distance in miles that a car has traveled in t minutes. Find and interpret f inverse of 70. Okay. So notice that one of our output values is 70. So the inverse function should take us back to the original. So then if we start with the output of 70 and we pass it through the inverse function, then taking us back to the original should give us 90. All right. So then f inverse of 70 should equal 90. So 90 minutes, yeah. Okay. So function g is given, find g of 3 and then g inverse of 3, okay? So g of 3, so when x is 3, the corresponding y, it looks like it's 1, okay? So then g of 3 should be 1. And then g inverse of 3. So if we take the output 3, where does it come from, right? So with the inverse, we're going to start with, when the output is 3, what's the corresponding input? So the corresponding input is 5. So g inverse of 3 should be 5. Okay. Let's see. So g of 3, the output was 1. Yeah, I think we got it. So given a function represented by a formula to find the inverse, I'm just going to kind of summarize this. So to find the inverse of a function, first it is a good idea to decide whether or not it has an inverse. We can do, there is a uniqueness test that we can do, and I'll showcase that. Yeah, so make sure that it is a one-to-one function, right? Now, if you can look at the graph, you can show whether it passes or fails a horizontal line test. I'll show you a uniqueness test to determine if algebraically if a function is one-to-one. Once you determine that the function is one-to-one, then you just write the function, replace f of x with y, and then we switch the place of x and y. So wherever there's a y, we write x. Wherever there's an x, we write y. Then we solve for y, and then that new function is our inverse function. Also, it's a good idea when we begin, go ahead and identify your domain, and then it helps if you can, just go ahead and identify your domain, and then when you find your inverse function, you can find the domain of that. So the domain of the inverse is the range of the output, and the domain of your original function is the range of your inverse function, right? Okay, I know I kind of mixed up the word a little bit, but hopefully you can get it. So find the formula for the inverse function. So first, let me see. So algebraically, to show that a function has an inverse, like I'm used to seeing it like whenever we have f of x1 equal to f of x2, we need to show that x1 equals x2. If we start with f of x1 equal to f of x2, and we finish with f of x1 is not necessarily equal to x1 is not necessarily equal to x2, then the function doesn't have an inverse, right? So this is Celsius as a function of Fahrenheit, right? So for instance, if we said C of F1, we want to set that equal to C of F2, right? And then the goal is we need to finish with F1 equals F2, right? So if we start with two different y values are equal, then we have to show that the corresponding x values are equal. If the x values are different, then it's not one-to-one, right? Okay. So then we would have 5/9 times, probably should have done capital F, but F1 minus 32. That's going to equal 5/9 times F2 minus 32, okay? So we can multiply both sides by 9/5. This is going to cancel this. So then we're going to have F1 minus 32 equals F2 minus 32. We can add 32 to both sides, all right? So this is going to cancel this when we do that. And we finish with our desired result that F1 is equal to F2. So that's how we show that a function is one-to-one algebraically. Sometimes we do finish with F1 is not equal to F2. Then we would say the function is not one-to-one, okay? So we've shown that this function is one-to-one. Okay. So let's switch the places of F and C. So let's say like we have F equals 5/9 C minus 32. And then let's solve for C. So first we can multiply both sides by 9/5. And that's going to give us 9/5 F equals C minus 32. Add 32 to both sides. Let me think. You know, actually, what we're doing is fine. I want to change my labels though. I think we could have just left it like, let me kind of back up a little bit, because what we're doing is fine, but I just going to change the labels. I'm going to leave this as F and leave this as C, and I just want to solve for F. I think that'll work. All right. So we can still do the same thing. Multiply both sides by 9/5. And we get F minus 32. And then add 32 to both sides. So degrees Fahrenheit is going to be 9/5 degrees Celsius plus 32. I think this is fine. Yeah. Let me see. For instance, the freezing point for Fahrenheit is 32 degrees Fahrenheit. That's going to be 0 degrees Celsius. So if we let C be 0, we get our 32. The boiling point for Fahrenheit is, what is it, 212? And in Celsius, it's going to be 100 degrees Celsius. 100 divided by 5 is what, 20? That's 180. 180 plus 32 is indeed 212, right? So yeah, this is good. Yeah, this is fine. Okay. So find the inverse function of this one. So this one is like a little bit more traditional. So okay, first we need to decide whether this has an inverse. So let's try our algebraic technique again. If we consider f of x1 and we want to set that equal to f of x2, we need to show that x1 equals x2, right? So then we're going to have x1 minus 3 under 2 plus 4. We want to set that equal to x2 minus 3 under 2 plus 4, okay? So then we can subtract 4 on both sides. We'll get our x1 minus 3 under 2 equals x2 minus 3 under 2. We could cross multiply here. Let's cross multiply and see what happens. So we get what? 2x2 minus 6 equals 2x1 minus 6. Add 6. If you add 6 and divide by 2, ultimately you get to x1 equals x2, right? That's what we wanted. So we can say that this function is indeed 1-to-1, right? Okay. So then so I'll keep working about here. If the original is f of x equals x minus 3 under 2 plus 4, we replace f of x with y, x minus 3 under 2 plus 4. We switch the places of x and y, so all x's and y's switch places. So now we're going to have x equals y minus 3 under 2 plus 4. Okay. So now we solve for y. I'll keep working over here. So first we can subtract 4 on both sides. So we'll have x minus 4 equals this y minus 3 under 2. I'm thinking cross multiply here. Keep in mind that on the left hand side, this is the same as this over 1. So then if we cross multiply, it looks like we're going to have to FOIL. If we FOIL, wait a minute. Actually, I don't think we need to FOIL. Don't FOIL. Would that help us? No, I don't think so. I don't think we need to FOIL. right? We can still cross multiply, but just don't expand it. So then we're going to say this x minus 4 times this y minus 3 equals 2. Then we're going to, we probably could have just flipped, but we're going to divide both sides by the x minus 4. So now we're going to have y minus 3 equals, now we got the x minus 4 on bottom under the 2. We add 3 to both sides. Okay. So then this is our inverse function. I forgot my domain, right? So my domain from the beginning, this is like a rational function. The domain for a rational function is all reals except any x that makes the denominator 0. So the domain of the original is everything except 3. So we'll say x is not equal to 3. That's the domain of f. Okay. So now for our inverse function, we got this x minus 4 under 2 plus 3. And this one, x cannot be 4. So the domain of our inverse is the range of our original. But that's it. That's the information that we need. All right. We don't really need much more than that. And I think I'm going to shrink it down to size. Okay. Okay. All right. So we got 2 over x minus 4 plus 3, where x is not equal to 4. Yeah. 2 over x minus 4 plus 3. So yeah, we're good. So find the inverse function of this. So first we want to determine if this is 1 to 1, right? So to show that it's 1 to 1, we consider f of x1 equal to f of x2, and we need to show that x1 equals x2, right? So now we're going to have 2 plus x1 minus 4, square root of that, equals 2 plus x2 minus 4, okay? We can subtract 2 on both sides. We'll get this and this. We can square both sides and we'll get this and this. Add 4, x1 equals x2. Okay, so that shows that this function is indeed 1 to 1. Okay, our domain, the only restriction is we can't take the square root of negatives, so that x minus 4 needs to be greater than or equal to 0. So then x is greater than or equal to 0. X is greater than or equal to 4. Right? Like I solved x minus 4 has to be greater than or equal to 0. So then x has to be greater than or equal to 4. So then that's what? The half interval from 4 to infinity. That's the domain of the original. Right? We're just keeping that in the pocket. Okay. So when we go to find the inverse, first we replace f of x with y. Then we switch the place of x and y. So the x's and y switch places. So now we're going to have x equals 2 plus the square root of y minus 4. And I'm just going to kind of keep working on this side. So now if we solve for y, first we can subtract 2 on both sides. So we'll have x minus 2, y minus 4. We've isolated the square root, so now we want to square both sides. Okay, that's going to come in handy. Okay. Now this squaring is, let's just go with it for now. If we square both sides, we'll have x minus 2 squared equals y minus 4. If we add 4 to both sides, we get y equals x minus 2 squared plus 4. So then f inverse equals x minus 2 squared plus 4. Now, this inverse is a parabola, right? Remember in the original, we said our domain was from 4 to infinity. We can actually find the range of the original as well. If we use transformation of functions, square root function generally starts at the origin, like the square root function is the top half of a sideways parabola. So then when we're done, let me see. So the range here, we went to the right by 4, and it looks like we went up 2. So the range should go from 2 to infinity. So then that's actually our domain of the inverse. It should be from 2 to infinity. Okay. Because we do need to impose that restriction on the domain, right? And if we just looked at the output, it's kind of hard to see, okay, well, what should be the proper domain there? So instead of focusing on F inverse, I went back to the original and I found the range of the original. You can just look at the graph. We started with the square root function, and through transformations, we went to the right by 4 and up by 2. So then if it's a square root function that's moved up by 2, so that means our range, which is the very bottom to the very top, is from 2 to infinity, all right? So once I identify the range of the original, then that's my domain of my inverse, right? Okay, let me paste. And I'm going to shrink this down to size as well. Some wind chimes out there been serenading me all night. It was kind of creepy. So like, you know, I kind of like put the deadbolt lock on the screen door. It's like a metal screen door. Just trying to let some fresh air in and left the door ajar. I just got to be careful because sometimes like creepy crawlies like to try to like sneak in the little cracks or whatever. So it was creepy because in the night I got all the lights out. You know, my dog is like, my little chihuahua is buried under the blankets or under me somewhere. So she's out cold, and the door kept creaking open like. I was like, and I knew it was the wind, but you know, it still kind of creeped me out. I'm like, damn, my dog's asleep, so she's not investigated. You know, and it's like pitch black. You hear, and it's like 3 a.m. You know, I'm getting a good sleep. I'm like, man. So I just kind of wait, and then you know, I was like, no, it's just the wind. It's just the wind. And then fast forward, I don't know, 45 minutes and some random time, another. I'm like, will you please? But again, I know it was the wind. I could hear the chimes, and there are other systems I have in place if it was somebody back there. So I knew it was nobody back there. And we don't have no negativity around here, so it was nothing like that. But it was still funny. Like I felt like if I was on a hidden camera show, you know, I'd be sitting here like, oh fuck, is there somebody there? And people just be watching and laughing. I think it would be hilarious. Anyway, but yeah, that was me at like 3 and 4 in the morning in the pitch black. It was so funny. Okay, I think we got maybe one more example here. Let's see. F inverse. We got x minus 2 squared plus 4. The domain of f is 4 to infinity, and the range is 2 to infinity. So that means that the domain of the inverse is also 2 to infinity. Yeah. Yep. I think we got everything else. X minus 2 squared plus 4. X minus 2 squared plus 4. And the domain is 2 to infinity. Okay. Okay. Given this graph, sketch the graph of f inverse. So when you're given a graph, the graph of the inverse is, we take our image and reflect it about the diagonal y equals x, right? So if we consider the diagonal y equals x, is it snapping to the grid? That's interesting that it's doing that. Let's go style. That's good. All right. So we want to rotate about that diagonal. We can like plot some points. So for instance, one point on the original is 1, 0. So then on ours, it's going to show up as 0, 1. You basically switch the x and the y. Let's choose a different color. Let's go this color. See if I have any other points. It looks like there's a vertical asymptote. So on ours, there should be a horizontal It looks like it passes through the point 2, 1. So ours, it should pass through 1, 2, which is this point here. It looks like it also passes through 4, 2. So on ours, it's going to show up as 2, 4. It looks like this point as well. And it kind of tapers, right? That should give us a sense. And so then we should have a curve, something like this. Let's try that again. They kind of stopped there, so we're going to stop there. But it's basically like we took their image and rotated about that diagonal y equals x. And then this in orange should be our f inverse of x. And so, like, again, if you have like a set of ordered pairs that are given or that you can find, once you have your x's and your y's, you can just switch those columns and then plot the new set of points, and that'll be the graph of your inverse. I chose green, that's okay. Okay. And so with that, that brings us to the close of chapter 3 on functions. And so momentarily I'll be loading section 5.1. We'll take a look at that, right? So with that, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care. Peace.